We saw how the application of Frossman's lemma gives a universal lower bound on the Hausdorff dimension of product of Borel sets. One wonders when this is indeed an equality. A good start is the upper bound given by the same theorem in Mattila's book, namely that the dimension, Hausdorff dimension, whenever we just write dimension, we imply Hausdorff dimension. So the Hausdorff dimension of A cross B is less than or equal to dimension of A plus the upper packing dimension of B. Now this object I won't define. It's not too difficult to define, but just technical, and we probably will not need it later either. So P there is not a parameter, it just stands for packing, and this bar on top is the upper packing dimension. If it was below the letters DIM, it would be the lower packing dimension. There is something called packing measures, but to define the packing dimension, you really do not need to define the measure as well. The way it's done in Mattila's book is that you define Minkowski dimension, which is very easy. It's just the counting of the number of epsilon balls that are needed to cover a set, and then taking them sup as epsilon, the radius of the balls goes to 0. And upper packing dimension is a modification of it for reasons that are described there. It turns out that the modification helps it become a bit nicer quantity. But anyway, given this upper bound and the lower bound, the obvious corollary is that if for the set B, dimension of B equals the upper packing dimension of B, this condition star, then dimension of A cross B is indeed equal to dimension of A plus dimension of B, as the upper and lower bound agree in this case. There are two practical and important sufficient conditions provided for when this is true, and I want to list them, and that will be the end of this video. Short and sweet, but also very, very applicable. Sufficient conditions for star. So the first one is if B is a self-similar set, which we have discussed extensively here, given by similitudes. So there are videos covering all these notions precisely, not just hand-waving notion of self-similar, but very precise mathematical one is provided in these videos, and with theorems that give Hausdorff dimension of such sets. But anyway, so if B is a self-similar set given by a finite collection of similitudes that have the open set condition, that also we have covered, then star holds. So dimension of B is actually equal to the upper packing dimension of B. So that's one situation where this will happen. As an example, we've seen that if you have this counter set in R1 with a dimension equal to 1/4, constructed in the usual manner, but with a different ratio of the removed intervals. So, and then we take B to be just A again. We had previously seen that its product, so A cross B, is actually a counter set in R2 with Hausdorff dimension equal to 1. Sorry, so 1/4 was the ratios removed, but the resulting dimension would be 1/2. And in this case, we see that this agrees. Of course, being self-similar, this could have also been deduced from condition 1 here, because the set is self-similar. The packing dimension and the Hausdorff dimension agree, so that in the theorem above we have equality from which we get that the dimension is equal to 1. Although we had also seen directly why the Hausdorff dimension of that set is equal to 1, and it was our first example of a purely unrectifiable subset of the plane. Okay, so what is my second sufficient condition for when the packing dimension agrees with the Hausdorff dimension? That is when the measure of the set B, so B, assume, has Hausdorff dimension T, and actually it has positive and finite Hausdorff measure, not 0 or infinity, and the lower density, these again objects that we have extensively talked about, the lower density is positive at all x in B. So then star holds, and then again the dimension of A cross B becomes equal to dimension A plus dimension B. Usually we're not used to seeing a condition in geometric measure theory required of all, only almost all. The reason I'm stating it here this way is that unfortunately we cannot easily plug at Hausdorff HT almost every x. This would still be correct if we said at the packing measure T, that dimension almost every x in B, but since we wanted to avoid definition or any reference to the packing measures themselves, so the more useful version would be this condition 2 here. So, and both of these are quite useful and in practice can be applied, giving us a whole lot of examples where we easily get dimension of the product set simply by adding the dimension of each item in there. Hopefully you will find this useful, and hopefully sometime in future you will remember this and say, okay, there I remember, I can easily claim that the dimension of the product is equal to this or that. So all in all, very useful. My next video will be focused on other applications of Frossman's lemma. So keep watching, and please also subscribe. You do it just once and that will be it. Thank you and have a wonderful day.